So hi all, my name's Camilla. I'm part of the On-Farm Carbon Advice team, and this is our webinar series. So thank you so much for joining us. Today's webinar is on the Low Methane Beef project with our guest speaker, Tom Granleese. Now, before we begin, I would like to acknowledge the traditional custodians of the lands and waters in which we gather today. I am on Wiradjuri country in Orange, and I recognise their continuing connection to land, water and the community. We pay our respects to elders past, present and emerging, and extend that respect to all Indigenous peoples here today. So today's session will be recorded and will be available on our website. So feel free to share that resource with anyone in your network if you find it interesting. There will be an opportunity for questions at the end of the presentation, but please feel free to put any questions in the Zoom chat and we will answer them at the end. I also have a very short survey at the end of the webinar just to collect some feedback about if you found it interesting or not. Let me introduce you to Tom Granleese. So Tom's based in Grafton and he's a research officer in the quantitative genetics team. He's also the Institute Director at Grafton Primary Industries Institute. He leads projects focused on genetic improvement in livestock. This includes the development of goat meat genetic resource herd and the New South Wales DPI component of the Low Methane Beef project, which we're hearing about today. His work centres on breeding programs that enhance producer profitability through informed genetic selection. Fabulous. Tom, would you like to take it from there? Can you share your screen?
Yeah, thanks, Camilla. And thank you to everyone for taking time out of your day to join this webinar series. I'm part of the Low Methane Beef project, which is a collaborative project with Meat and Livestock Company, their donor company, Angus Australia, University of New England, and New South Wales Government. So a little bit about background about methane for those who don't know a lot about methane and how methane fits into the ruminant production cycle. So methane comes in the form of gas, and it's part of the rumination process in ruminant species. So whether it's giraffes, alpacas, cattle, sheep, goats, anything with a rumen has this process. So basically, if we think of methane, its chemical formula is carbon and 4 hydrogens, so CH4. So ruminant species, they eat plants which contain carbon, and as they ferment the cellulose or the starch, a byproduct is methane. That methane's breathed out, so 95% of methane produced from ruminants comes out of the mouth, and that methane hangs in the air for about 12 years before it's oxidized into carbon dioxide. And that carbon dioxide, so if we're following this little cycle, the carbon dioxide is then eaten up by plants growing as part of photosynthesis, and then the plants breathe out the oxygen, and the carbon is sequestered back into the plants and the roots. So I tell my kids that we breathe plant poo because that's what they're pooing out, part of growing. So another way to look at that is we can look at it from an efficiency point of view and a different kind of diagram. So cattle or sheep eat cellulose, hemicellulose, pectin, starch, mainly cellulose and starch. So that's grain and grass. And they can get some energy directly from, but mostly they have to ferment that feed source to actually get their energy source. So what happens is they eventually create volatile fatty acids, and those VFAs are the energy sources for the host. And the byproduct of it is that during fermentation, we have dihydrogen and carbon dioxide being created, which then is the methane and the carbon dioxide. So another way to look at this is just from a chemical formula point of view. And you'll see that it's just 3 chemical compounds being reorganized in the body. So those 3 chemical compounds are carbon, hydrogen, and oxygen. So C, H, and O. So we do that diagram all over again. We can see that we've got combinations of C, H, and O that the animals are eating. And they are converting them into other forms of C, H, and O. Again, we have other, we don't need to remember all the numbers, but just remember that we're just moving the carbon, hydrogen, and oxygen into different forms. And again, the energy source combination of C, H, and O. And then we've got our dihydrogen and our carbon dioxide. And so there are carbon atoms that are binding to these dihydrogens, forming the methane. So methane is linked to efficiency. So every mouthful of feed eaten by a ruminant, there is between 5 to 15% or 7 to 15% of that. Each mouthful of feed is lost through this fermentation process. And so the idea is that methane research in livestock species is not new. There was science first developed in the 1910s, 1920s, looking at methane as a lost energy source. So this isn't new science. It's just that we've become more aware of methane being 28 times more potent in the atmosphere than carbon dioxide. So it's sort of a win-win, because if we start looking and selecting for methane production, we can both link that to feeding efficiency in ruminants, but we are also doing our tiny little bit for the total carbon entering the atmosphere. And yeah, so it's basically how do the carbon, hydrogen, and oxygens get partitioned during that rumination process. So we would like to find the 5%ers and breed from them. So is there genetic variation in methane production? The answer is yes. There was preliminary studies done for genetic variation in the teens decade. And so we know that if we measure enough animals for methane, we can start to select and make genetic progress in that. So remembering that genetics is a permanent and cumulative solution to any trait improvement, really. Yes, we've got nutritional sorts of ways of mitigating methane in livestock, such as feed additives. But that's only temporary, and they have to be on feed, and there needs to be a feed mixer wagon go past every day, and it's expensive. Whereas the genetic part, well, that's in all conditions, on all pastures or feeds, and it's permanent, and it builds on it each year. So modelling suggests that we can improve or decrease methane production without sacrificing any traits, any of the other production and reproduction and health traits, by 1% per year. So it's 1% this year, 2% next year. In 10 years' time, it's reduced 10%. In 30 years' time, it's 30%. So genetic gain is a slow build, but it's permanent. And over time, it makes a really big difference. So we don't have breeding values for methane yet. And that is because we haven't measured enough animals. So if we're to create breeding values or genetic improvement, we need to measure thousands and thousands of animals. So these initial studies only measured up to 1,000 animals. And we realise that we need as many as we can get. But when I say thousands, I'm talking up over 10,000 records on individual animals before we start being able to start to estimate and create genetic change through the use of breeding values. So this is where the Low Methane Beef project was set up. So we had two wonderful what we call reference populations. So reference populations being populations that are very well recorded. So we know who mum and dad are. We have a DNA sample on them. And then we start measuring animals born all at the same time in large cohorts. So then we can take out the environmental influences of how an animal performs and start looking at how the animals deviate within their contemporary group to then be able to start estimating the genetic differences between animals and family lines and even breeds. So we have the Southern multi-breed population, and then we have the Angus sire benchmarking program that we're measuring these traits, the methane traits on. How are we doing it? We're using, there's quite a few different ways to measure methane now, but we're using what's called the green feed machine. So the green feed machine is what you can see here. The animal walks in, and to get the animal in, so this is all voluntary visitation. So it's really hard to get animals to come and stick their head in a buzzing box out in the paddock. And so they need a treat. So what you can see there is a feed bin here. So prior to all of them seeing this machine, we train them to love grain. So that's their lolly. So they stick their head in, and then there's a RFID reader, which will check if the animal's been in before. So we have some really greedy animals that go in every 5 minutes, and they say, no, you're not getting lollies this time. You come back in 5 hours' time. So all this data is connected to the cloud, so we can sit at the desk and change all the settings to help encourage them to come in or block the really piggy cows. So what happens is if it is their time to get recorded, they're in there munching on grain, and what happens is there's a fan up here and it sucks the air through some holes and up here, and they go past the carbon dioxide and methane sensors, and then that data gets sent up into the cloud where we can access it in real time. So that's a diagrammatical one. This is a picture of one out in the paddock. And we can also, at the same time, if we're measuring in the feedlot, we can have the animals on these grow safe or feed intake units, and that tells us how much food they've actually eaten in the day. So the thing to remember about methane is that the amount of methane they eat, most of it the amount of methane that is produced comes down mostly to how much they eat. And how much they eat comes down to how big they are. So bigger animals eat more food. So if we easily wanted to reduce methane, we would just reduce the mature size of animals. However, we want to find the efficient animals. So to liken it to humans, we want to find the animals that eat or would only have to look at a Mars bar and they put on weight. Whereas I'm probably a little bit guilty of eating whatever I like and not putting on any weight. So I'd be a cull in the livestock world. So that's why it's we're measuring feed intake as well on the animals in the feedlot. So I'm in charge, however, so University of New England's in charge of measuring steers in the feedlot. So they get the easy job because they're a bit bored in the feedlot and they like to stick their heads into buzzing boxes, otherwise they don't get food. Whereas out in the paddock, which is what I'm in charge of, we measure the steers' sisters out in the paddock. And so there's a lot of different distractions out in the paddock. So it's much harder to get the animals to come into voluntary visitation of walking into a big steel set of yards and stick their head in the green feed machine that's buzzing away. So it's been a challenge over the last 4 years, and we've got better and better at it, but we've made a few mistakes in our learnings along the way. So yes, we've got the feedlot and we've got the pasture. So I've got some, no, I don't have videos, sorry. I'll just go back a step. So to begin with, we actually we make the panels really wide, so it's not so claustrophobic for them when they're in the paddock. And so it's not such a foreign concept to be sticking their head in here. There's plenty of space to move out and make sure that the lion doesn't eat them because they're quite wary. Over time, we start to as they get addicted and hooked to the grain and they know there's treats in there, we start to narrow the panels up so that we don't get what's happening in the middle picture where we have two heads in the box at once, because if we have two heads in the box, there's twice as much methane. We get a false reading. So we want them in a nice narrow panel, so we like a 70 centimetre race, so that there's not any cross-contamination. So you can see that big fat Hereford there is trying to knock out that little Wagyu. I think persistence paid off in the last picture because the Hereford went away. But that's all in the training period. So what we've got here is a graph of a few different sites that we measured, and we've got different breeds by different colours. And if they went in and got recorded, they've got the little lines across, and then we've got, if they didn't get recorded, they didn't come and voluntarily come in and put their head in and stay in that box for 3 minutes, then they had no record. So you can see that there was variation in trying to get animals in and recorded. So the idea is that we need 30 records over a 4-week testing period. We need 30 records of these animals to get a reliable methane baseline measurement. And so one measurement is if they have their head in the box for 120 seconds, 2 minutes. Now, if they lift their head up and look around, that's it. The measurement's done. So if they're really nervous and flighty, so Wagyus and Brahmins are particularly tricky because they're always up looking around, making sure that a lion or a tiger is not going to come and eat them. So yeah, they visit, but they don't keep their head in for long enough, which has been a real challenge. So if we have a look at this next slide, if you look at the Wagyus, the green ones, we can see that early on in the project, we had a lot of trouble keeping them in the box, in the green feed machines. And then for the Wallingbar, we've got the Brahmins, so the yellow box. And we can see that in one particular year, they were quite low as well, a bit like the Wagyus. But so that was S. So they were the first cohort recorded. We learned we made a lot of mistakes and learned from that. And we can see in the second year of recording, we had much better visitation. And as time has gone on, we've got better and better. So in regards to, then we get the methane records, and what happens is, what we've found is that the cattle are emitting different concentrations of methane at different times of the day, depending on when they've eaten. So we can see in this graph on the left that they have quite a high amount of methane, and then by 6 o'clock in the morning, when they're starting to go out and graze, they're actually having the lowest dip in the day, and then they sit down and ruminate a bit, and it comes back up, and then they go to sleep at around sundown, and then they're ruminating quite a bit and releasing that methane. So, so given that these visitations are voluntary, some animals will come in, they'll come in 20 times a day if they were allowed to, but we limit them to 5 visits a day with sort of 4 hours between each visit. And so, but some animals only come in at 7 o'clock. So that's a real challenge in analysing the data, because they're coming in at the lowest time of the day, and that would be a misrepresentation. So what we had to do was we had to put a diurnal correction into the data, so we get the raw data, and then we have to correct it so we have somewhat of a flat line. So instead of having this diurnal pattern of feed of data coming in, when we analyse the data, we can standardise it using a fairly complex mathematical formula I won't bore you with. So we've got the data, which is great. And so we are into our 4th and final year of this project. So we've exposed by the end of this year, we'll have exposed close to 8,000 animals to green feed machines. Obviously, not all of them come in. So being geneticists, we're always hungry for more data. But now that we've actually got enough data to create genetic estimates, we actually need to think about what trait definition we want to go with, because there are 4 trait definitions we can go with methane. So there's methane production, which is basically the raw amount. So bigger animals emit more methane. So that would be grams per day or tons per year or a unit like that. Methane intensity is amount of methane per product unit. So how much methane was emitted per kilogram of, say, beef created. Then we have methane yield, which is the amount of methane per kilogram of feed eaten or a tonne of feed eaten. And then we have methane utilisation. So that's more the dollar per hectare. So industry, so that's part of this process is the wider industry need to get together and work out what trait definition we go with. Pretty much everyone is leaning towards intensity or yield, but we do need to finalise that decision. So we've got all this data. So we put, so to get genetic estimates, we need to, so genetic estimates are mathematical calculations. So we put that into a linear mixed model, and we have to simplify it a bit. So to predict an animal's genetic merit, here's the model where X is a vector of fixed effects, where we take breed and their management group and their age into account. And then we have the animal effects and the genomic relationships. So we have DNA on all these animals. So what we have, we move over to the, don't worry too much about that. I don't know if there's any maths nerds in there here, but we'll jump over to the table. So we've got, the first thing we want to know as geneticists is there variation? And if there is variation, is it genetic or is it environmental? And so what we can see here is that, yes, we have lots of variation, and the heritability is how much genetic variation divided by the total amount of variation. So it's 291 divided by these two numbers put together. So the heritability is 0.36. So the heritability means that 0.36 of a phenotype is dictated by genetics, and the rest is through the environmental factors. So we would call this methane production mildly to strongly, somewhere in there, fast, medium, fast, cricket bowler, heritable. So we can make lots of progress in this trait, which is cool. Another question that we have is methane produced in the feedlot the same as methane produced in the pasture, given that any given time about 5% of animals are on the feedlot and 95% are on pasture. However, measuring methane is much easier in the feedlot than it is in pasture. There's more efficiencies, it's cheaper, we get more animals measured. And initial estimates say that it's about a genetic correlation of about 0.6. So it's suggesting that it's not the same trait. So methane produced in the feedlot is not the same as methane produced on pasture. So that's a very interesting outcome. Now we need to delve into a bit more why. So that's another question that we need to answer. Given that we've only just got enough data to start analysing, we've only just started analysis, and got way more questions than answers at the moment. So methane is associated with average daily gain. So average daily gain, the genetic correlation of about 0.44. But we can see here that we've got animals here in the top left who are desirable. They're gaining faster. They're gaining faster, but emitting less methane. And then the other graph we have here is daily feed intake. So we want animals who are eating less but producing more, but also producing less methane. So we'll be looking for animals in this bottom quadrant, and we can actually see we've got an animal down here, which is a total outlier, which is an animal that would change an industry or a breed really fast. So that's exciting. Here we've just got a plot of Angus sires, their index, so their total production index versus their methane breeding value. We can see we've got some very high indexing animals. So that means, do we have to sacrifice production and reproduction and all those economic key drivers while reducing methane? Well, generally speaking, if we were to do that, we'd probably be breeding more higher methane emitting animals. But in this quadrant, we can see that there are animals that are breaking that correlation. Another, cause of concern was if we're breeding more efficient animals, we're breeding them leaner and we can't get intramuscular fat. And it has proven to be sort of true, but there are still outliers where we can breed less methane, so less methane over here, and higher marbling animals. So because we've measured these animals and we've identified their genetics, we can we can progress in all the desired directions. So that's super cool. So I'm just about at the end. So just to summarise, it's quite an expensive project. It's a $15 million project over 4 years, but we're setting up the baseline for providing tools to enable that selection of low emitting cattle, which is permanent and cumulative. It's different to the feed additives. I probably need to reheat this slide, but we're probably 85% of the way or 75% of the way in, and the data analysis has begun and we're well down the track. There's no difference in breeds for efficiency, but there's lots of variation within breeds. So if anyone's asking what's the best breed, there is no best breed. It's like picking a World 11 of soccer. You have lots of different individuals from lots of different countries. And the data analysis is tricky, particularly in the pasture data. So I'd just like to bring to your attention, every year we have a big beef efficiency day where we present all of our updates. We also get to eat some beautiful steaks. It's a free event, and it's a really good day. And then we get to go out to Talimba and we see the animals at the feedlot with the feed intake machines and the green feed machines in real life. So it's always a good day. So there will be invites that go out for that. And just finally, some challenges in the future. So we need to do more and more. So we've only just started. If we're thinking about building a house, we've put the slab down basically. We need to keep going until we're ready to move into the house, but it's a really solid foundation. The cool thing is about measuring on the Southern multi-breed and the Angus benchmarking is that they've measured all the other production traits. So we can actually start to see what the relationships are with other key production traits. So if we were selecting solely for other production traits, what's the correlated response to methane, and vice versa. If we went super hard on methane, what are our what would happen to all the other traits? We need to build methane into selection tools, so indexes. So indexes are a single number with a whole bunch of, it's a bit like the UAI at year 12. It's just a single number to say how good they are in a given production system. But you can be good for particular traits, or you could have done really well in maths, not so good in biology. We could have done really well in English. So there's lots of different ways to be a high or a low indexing animal, a bit like the UAI. But we need to work out how we build that into the selection indexes. And then we also need to understand some biology. So we've been collecting rumen fluid on all these animals, and we're seeing if we can see if there's any relationships with the microbiome, ammonia, VFAs, protozoa, because they're much cheaper to measure. So it's about $1,000 an animal to measure for methane on these machines. It's about $100 to do the rumen fluids and analyze. So if we can get like the gold star standard on these machines and then look for some cheaper secondary measures that inform, then perhaps that might be a way. We have a small amount of gold star measurements, and then we have lots of other like heaps and heaps doing the secondary cheaper measures. The team, we've got a big team across all the organisations, and there's a lot of people out in the field. They've got to be at the machines every single day of the week, and we're testing about 300 days of the year. So that's weekends and a lot of time away from family. So a big shout out to all the technical officers who are collecting data out in the field. And just a list of acknowledgements of all those people as well, and the funding partners. So, that concludes, but happy to take any questions or comments.
Fantastic. Thank you so much, Tom. That was fabulous. Are there any questions from the room? So I have one. Tom, I was lucky enough to go to Trangie last week and see the green feeders in action. Is there anything that you're thinking about giving, the lolly that you were talking about in terms of the grain? Are you thinking about mixing that up with some sort of salt lick or something as well, just to try and get the non-visitors to come in? Or can it be a learnt behaviour?
It's a good question. So we haven't really deviated around the pellet. So the salt, we were just a little bit concerned about the wear on there's a lot of metal in there, and whether that would cause unnecessary erosion. So inside that feed box, there's a little cup that tips over. It's a lot of mechanics, and I know there's salt already in the grain, but salt particles, like loose lick salt, we got a bit nervous, and a lot of it would fall through the cracks of the grain. And we've thought about a lot of different attractants, and we've sort of settled on the grain pellet. Some people use loosened pellets. Mm-hmm. I think in a cruel way, using water as an attractant would be the most effective, but
Okay.
That'd be too tricky and probably an animal ethics
Yep.
issue. So this is sort of where we've settled, and we're feeling pretty good about where we're landing now in terms of visitation. So feedlot gets about 90% records on their animals. In the pasture, we're at about 75% to 80% now. At the start of the project, we were sort of 65% in the feedlot and 45% in pasture. So we've refined things to, which has been a major learning throughout the process. So, yeah.
Awesome. There are a couple of questions in the chat. Michael, do you want to come off mute and put your camera on? And then Sue, I might get you to go afterwards.
Yeah, great presentation, Tom, and thanks, Camilla, for taking the initiative. It's a good initiative too. So well done. Just interested, like there's a lot of work done on the Bos Taurus cattle, Bos Indicus cattle. Obviously, they make up a bigger proportion of the herd. Is there a similar project underway for that?
Yes. So there's a southern component to this. There's a northern. So repronomics. So University of Queensland are in charge of doing the northern cattle at the moment. Both of those projects are just about to wrap up, but then after that, the zero net emission CRC will take up the slack and will continue. That's about an $8 million project that will continue to measure both on northern and southern cattle.
Okay, and similarly, are there similar results coming out in terms of genetic variation amongst the different breeds? Yeah.
Yep. Yeah, quite similar, which is pleasing to see. And again, there's no best breed, but there's stars within each breed and high emitters as well. So and that's what we expect that as geneticists. There's always good ones, there's always bad ones. We just need to measure it and quantify it, so then we can select for it.
Yeah, excellent. Well done. Thank you.
Thanks, Michael.
Thanks, Michael. Sue Mortimer, would you like to come off mute and ask your question? Thank you.
Okay. Hi, Tom. Nice presentation, as usual. Excellent. Tom, you mentioned the cost of measuring methane emissions from the cattle using the green feed machines. So, and for the extensive systems that beef cattle find themselves in, do you see any other measurement tools that are there or on the horizon for measuring methane in cattle, and whether these tools could be eventually used on farm to augment the data that needs to keep genetic evaluation rolling on?
Yeah, so great question, Sue, because yes, it's cost prohibitive for for an average seed stock producer to be measuring that. So there are a couple other technologies. I didn't want to get too bogged down in detail, but there are sniffers. There are a couple of companies like Optiway are trying to validate their methane sensors as well. But again, these are all sort of voluntary. We've had conversations about looking at getting spot records. So a spot record being just one record of animals in a crush with a portable green feed unit. There's also the New Zealanders are using the portable, the pack chambers, portable accumulation chambers, where they sit in a dark box for half an hour. Mm-hmm. So there are other ways. I'm quite hopeful for the rumen sample. It takes only 30 seconds to take a rumen sample, and then we take those results back to a lab. And so to answer your question, Sue, I think there's lots of different ways to measure methane. As time goes on, the technology becomes cheaper, and that's science. We develop and validate cheaper ways to do things. Given we're starting sort of at the start, it's always going to be the most expensive. But I think like the green feeds is probably the best way to measure at the moment. And then we use all these other measurements in a multi-trade analysis to inform that one green feed. breeding value.
Thanks, Tom.
Thanks, Sue.
Great. Now, are there any other final questions? So we might wrap up there and give you 20 minutes back in your day. In the chat, I have just put a little link for our survey. It's only a couple of questions. We'd love to hear from you. Again, this session is recorded and will be available on our DPI webinar series website. And I just want to say a huge thank you to Tom for making the time today and for, you know, being okay with me bugging you for months on end to come and do this. And thank you all for your time. I really appreciate it.
Thank you. Thanks for being an attentive audience, and hope you have a good rest of the day. And thanks, Camilla, for organising.